Impressionnant. Totalmente. Yeah, I like that stuff. Okay, so I'm going to begin. Should I put on the lights? Okay, so I'm just going to begin. So the business of this course is usually called computer science, although it is not so much a science, but you can call it engineering or an art, right? But also it's not so much about computers. The goal of this course, which is coding logic, is not to learn a specific syntax of a particular programming language. Learning the syntax of a particular programming language is quite trivial compared to the knowledge of the structure and the implementation of computer programs. Um, and so, if you are going to implement a computer program in any of the programming languages, there are documentations that are readily available, and so you do not really need to. There's no need to pretty much memorize syntax as your first step in learning coding logic. Coding logic is about three things. I categorize them into symbols, constraints, and search. So, symbols is how we represent the world, constraints is how we define the boundaries of what is possible, and search is how we find the solution within those boundaries. So, we're going to be so one of the huge differences between, let's say, computer science or engineering and any other form of engineering is that um, in, let's say, mechanical engineering, if I want to connect multiple, let's say, pulleys and levers together, there'll be a there's a point where it gets ridiculous and unnecessary or useless because of the amount of friction that will be generating per lever, and at some point our system is going to be useless. Or if we are talking about electrical engineering and we are connecting, let's say, a bunch of electrical devices together, the noise produced per device would greatly affect our system. So at the end of the day, there's a physical constraint to what we can do and how we can combine those components. And of course, if you're looking at it from the hardware level, there are still constraints, right, of how fast your microprocessor can process data and so on and so forth. But when we have abstracted to software or computer science, we are now dealing with idealized components, and so the the limitation is basically as much as you can think. So whatever you can think, because we are dealing with idealized components, we can achieve in computer science or engineering. I'm going to be briefly talking about the heuristics for programming. To think like a master engineer, you must adapt a specific set of mental habits. I to categorize them into three. The first is the principle of representation. So behind every program is a great representation of data. And if you choose the right way to represent or to describe your problem, the logic is often simpler. The next thing is the power of abstraction, which is, of course, there are other areas in not just engineering, in every field that deals with abstraction. But computer science, there's a unique way that it works in computer science. And so you must not bog yourself down with how you achieve what you want to achieve, but you should focus first on what you want to achieve. And so there's this concept called a black box abstraction, which means you know what is going in, you know what should come out. So basically, you know your inputs, you know what should be your output, but what is going inside the box, what is happening inside the box, the gears in the box are not your concern yet. So that's what is called the black box abstraction, and we'll talk more on that. And the third is the storytelling requirements. So there is this principle that a computer program is first written to be understood by another engineer or a man, and coincidentally to be understood by machines. And so any program that cannot be understood by another programmer would or programmers generally would eventually also not be understood by the computer. So why does this course matter? So the reason why this course matters is because this course emphasizes not just on programming but the fundamentals of computer so-called science, computational thinking, algorithms, programming languages, and how these things fit together in order to develop and design programs. And we'll go beyond that and also consider how to analyze algorithms, how you pick algorithms, and how you design them, and so on. So we're moving to so let me give you an example of the black box of the black box. Let me give you an example of the black box abstraction. So, for instance, we want to perform square root operation. In mathematics, we usually deal with what is, that is what is true. But in computer science, we deal with how to. So when talking about something like square root in mathematics, y is equal to the square root of x such that y squared is equal to x, where y is greater than or equal to 0. Right, that's very simple. That's very clearly stated. Just stated to you what square root is. But then programmatically, if you want to get the square root of the number, or you want to write a function that gets the square root of the number, you cannot simply describe what is, but you have to describe how to. So how do we get the square root of the number programmatically? So we make a guess g, right? And we improve our guess by averaging g. And let's say, okay, we are trying to get the square root of x. So we make a guess g, we improve the guess by averaging g and x over g. And that gives us an output. And then we keep improving that output until our output is good enough. And good enough is what is defined by fixed points. So which is also what is in the box, what is in the so-called black box in the black box abstraction. So we have inputs entering the black box, we have outputs leaving the black box, and then we have a fixed point function in the black box. For instance, this square root operation. So for instance, we want to get the square root of 25. We know that 25 is going in, we know that 5 is coming out. We want to get the square root of 81. We know that 81 is going in and 9 is coming out. What's happening inside the black box that is turning 81 to 9, 25 to 5, and so on is not our concern as of now. So let us begin talking about. Let me share my slide that I prepared today. So coding logic, how computers think. So today we are going from sand to Instagram. So And sound is just me being funny. Is actually transistors, but it's also not that far off since the transistors we're talking about are silicon transistors. So our learning objectives to understand computers, convert binary to decimal, ASCII and Unicode, RGB colors, abstraction and IPO model. So what is a computer? So computer is an electronic device that processes inputs using algorithms to produce output. It is also the same idea of the so-called black box. We know our inputs, we know our outputs, and then the computer makes that process. And there's also what's called a chain of processes. That is, a process can also output another process. So let me do a little bit more on the black box abstraction since it's also quite telling here. So programming languages are built out of primitive objects, and then we have primitive procedures, we have primitive data, and then we also deal with the means of combination and the procedural composition and also construction of compound data, right? So means of abstraction, the procedure definition, simple data abstraction, and when we get to high order procedures, the line between what is data and what is procedure is actually now very debatable because you can have the output of a high order procedure is another procedure. So mostly we think of input and output as input data, output data. Procedure is in between, but you can the output of a procedure can also be another procedure, and the output of that procedure can also be another procedure. So data or procedure as data, data as procedure, however you want to think about it. So the computer is made up of millions or billions of transistors, and those transistors are can be conceptualized as switches. So there is a bi-state device that can either be in an on state or in an off state, or some people say zero or one, or true or false states, right? So the amount of data that we can, so for instance, we have if we have two transistors, right, or we have two switches, the amount of data we can represent with those two switches is 4. So we can represent 0, we can represent 1, we can represent 2, and lastly we can represent 3, right? And so there's also a formula that the amount of data that you can represent with an n bit with n bits is 2 raised to the power n. So basically everything we do on a computer goes down to comes down to transistors, comes down to ones and zeros. That's at the in the final analysis. That's all the computer understands is ones and zeros, and those states are being held by billions of transistors. So that's the idea behind sound to Instagram. So before we get to Instagram, starting from transistors, which is we're talking about silicon transistors, probably a MOSFET, which is silicon doped with metals. And so lower level of transistors, we can even go lower than that and go from physics, talking about electrons, and then we go to transistors, and then we can go to electrical circuits, right? You can go to and then from digital circuits, you can go to uh, devices like chips, microchips. You can go to microarchitecture, then computer architecture, then From there, we can talk about operating systems, and lastly, we can talk about application programs like Instagram. So there are different layers of abstraction, and if you want to go down to the physics level, fine by you. But if you're going to be doing computer science, you really do not have to worry much about that, right? So yeah, so that's the idea from sound to Instagram, is that this the computer is not this sort of mystical or magical device. It is like that's how it goes. It just goes from transistors to that. So I don't want to talk about the physics of how the transistors actually hold or actually form this great thing that we all are experiencing right now. So the composition, okay. So binary basics. We're talk about binary basics. So because all our programs get compiled or interpreted to machine code, which also gets interpreted but down to binary. And so binary is very important because this is all the computer really understands. And so ASCII. So for instance, when we type in three, because humans we have decided we have decided to be familiar with decimal. And so we have decided that we'll do our own mathematics and our own calculations using decimals and using decimals. And so, um, sorry, give me a minute. And so when we on our keyboards we press one or any of these characters, alphabets, it is basically just another layer of abstraction that compiled down to gets compiled down to machine code at the end of the day. And so 1, 2, 3, ASCII is just a system of converting or a standard for converting these our numbers and letters and symbols down to machine code. And so everything goes down back to hexadecimal. And so this is the ASCII table. So for instance, if I click press 2, that gets converted to 2 3 in hexadecimal. So that's OX. Or if I press the letter B, that gets converted to OX42, which is hexadecimal, and eventually goes down to binary. So even colors, and for some of us use those editing software, and those colors to have their own standards, their own programming standards. So RGB, for instance, is represented in red, green, and blue, and they are up to 255. So 255, 255, 255 gives you white. 000 gives you black, and in between you can represent all shades of colors using the RGB um, standard. So at the end of the day, everything is code. The colors you are seeing on the screen is still code. The pictures that you send, maybe using JPEG or PNG, still those are still standards, and those are still levels of abstraction, and everything still goes down back to binary for the computer to be able to understand what we are trying to communicate. right? And so this is a quick example of, okay, so hello, how many bits do you need to represent hello, right? So okay, in ASCII, right? So H, if we convert to hexadecimal, let's go back to this table. So H, small letter H, that's 0x68, and each hexadecimal is 4 bits. So which means H will give you 8 bits, and so we need 8 bits for H, 8 bits for E, 8 bits for L, and so on. And so at the end of the day, we need 40 bits to be able to represent hello. So I've talked a lot about abstraction already. On the input processing output model, I think I've also spoken about that. And so yeah, I already told you for n bits or for n switches, how many possible combinations or how much data can we represent with n bits. The general formula is 2 raised to power n. So if you have 4 bits, we can represent 16. Um, we have up to 16 combinations, and we can represent up to 16. We can basically represent up to 16 different information. So, for instance, we have a 4 bits. So that's 0 1 0 1 0 1 0 1, right? And we can combine that in different ways. So 0 1 1 1 0 0 0 1, and get up to 16 combinations. And we can represent even 1 to 16 with that, right? So this is a quick little um, let's say problem. So MTN has 80 million Nigerian subscribers. How many bits does MTN need to give each subscriber a unique ID? So our output is want our big N should be 80 million. So that's the amount of information that we want represented. And so what's the N that we need, the small N that we need to be able to get to 80 million? And so we can just do, we did logarithm in secondary school. And if you have not done logarithm, you can look up how to do logarithm. And so if you do log of both sides, you get n is equal to log 2 base 2 of 80 million, and that gives us 26.25. And so approximately 27. So if you use 26, it will be less than enough. But if you use, so all we need is 27 bits to be able to get um, as much as 80 million. And so 27 bits can be converted to bytes. If you divide by 8, which should give us about 7 bits. I mean 7 bytes rather. So homework for this section: convert each letter of your first name to ASCII decimal value into binary. How many bits in your name? How does this compare to a classmate? And so this is just basic introduction. And so I'm going to be going to the nitty gritty of what we have today. So the grand illusion of abstraction, I've spoken a lot about this already. So let us just go down to, okay, I've also spoken about binary. So yeah, the big O notation. So the big O notation is basically to measure the shape of time and how the runtime of an algorithm grows as the input grows as well. So when we're talking about big O, right? So there's big O, there's little o, there's even omega, right? But let's not get too far ahead of ourselves. So we have constant time, which is the ideal, right? That the time doesn't change. You can look at the graph that the time doesn't change. Constant time means the time doesn't change with the scale or the size of the input data. So even if you have one data, the algorithm will take, if it takes, I don't want to use seconds because, so basically if it takes 1 unit of time, right, for 2 bits of data, it will take the same for 1 million bits. So that is what constant time means. Logarithmic time, you can look at the graph, and so it looks linear for very small values, but as the values get, so it begins to have this sort of what will I even call it? Basically, you can look at the graph, but which is the second best time complexity that we could have. And so most of our algorithms are in the logarithmic scale. Most of the good algorithms or the faster algorithms are in this logarithmic um, time complexity. And so linear is that if that it scales linearly with, or directly proportional to the input size. So if you have 10 and let's say the time was, I don't like to use time, I will explain the reason why, but let's just use that for now to make it easier to understand. So let's say it took 10 seconds for, which is not how it works. This seconds, this thing that I'm using is not how it works, but I'm just using it to make it easier for you to understand. So linear means if it takes 10 seconds for 10 bits of data, then to take, let's say, 100 seconds for 100 bits. That's linear. That's not how it works with the time, but let's just use that for now. Linear arithmetic, which is something multiplied, so n log n of that scale, which is, that's worse than linear. Quadratic n square. So if I have, so it squares as my input increases, right? So if it was 2, it will be 4. When we get to 4, it will be 16. You can see how bad that is, right? So then exponential is the worst case, which is 2 raised by n. So if I have 2, it will be 4. If I have 4, 2 raised by 4 to be, that 32 or what? I can't even think. 16. Then when we get to 5, it gets to 32 and so on. So yeah, so an example of an algorithm or two algorithms that have this time complexities is binary search. So binary search is on the logarithmic time complexity. It has logarithmic time complexity, and we'll still look at that. While linear search, as the name implies, is linear. So the amount, yes. So instead of using seconds, let's use steps, right? Because there are a lot of things that actually affect the time per step of a computer program. No, not really a computer program, but what's it called? A machine cycle, basically. And so because it doesn't always take the same amount of time. So let's that's why it's not good to use seconds. That, oh, if it takes 10 seconds, no, let's use steps, because the amount of time per step of a machine cycle is not always the same. So the machine cycle might take 1 millisecond, and you might, that same machine cycle might take, the next machine cycle might take less than or more than that. So time is not constant when it comes to machine cycles, and the other that is beyond the scope of this particular course. But I've forgotten what it's called. The time, there's a name for it. This machine cycle time. I think it's cycle time. So linear search, as the name implies, will take 1 million steps for 1 million items, and binary search would take 20 steps for 1 million items. That's ridiculously good compared to linear search. So, for instance, an example of linear search is we are searching something one by one. So, for instance, if I give you a book, right, and I say, oh, help me find, or I give you my notebook and I say, help me find where I wrote um where I wrote canon in my book. And then you go from the first page, you look at each word one by one, one by one, one by one, one by one. And so this big O we are talking about here is worst case scenario. So the worst case scenario, you can be lucky and that canon will be the first word on my book. And so it will just take you one step, right? Even though there's a million items on that book, right? But worst case is that that canon is the last thing on that book, and you have to go through every single word in that book, which will take a million steps because there are a million words in the book. But binary search, and there's also a, what would I call it, a requirement to be able to do binary search. And the requirement for binary search is that the data space, or the what would I even call it, data set is already sorted. That is, there is uh it's already sorted. Basically, for instance, now a dictionary is sorted because it is A, B down to Z in that order. So if I tell you, help me look for mango in the dictionary, no, yeah, you're not going to be stupid enough to be starting from the beginning because you know that's where A is at, right? And so you may probably just put your hand at the middle and then you say, oh, I landed at K. It means M is on this side, and then you start looking for M on that side, right? So that's how binary search works. It's only that you need the data to be sorted before you can use binary search. And that, even though that seems like a lot of work, it's ideal for you to have sorted data once and then keep using binary search, right? So you sort data once and you don't need to do that ever again and just keep using binary search than doing something like linear search that will take you one worst case a million steps, or that's right, that has O of n time complexity. So this, so let's see this question. If an algorithm runs in O of n squared and n doubles from 1000 to 2000, how many times slower does it become? So this is quadratic, right? So if it goes from 1000 to 2000, how many times slower does it become? So so if it's at 1000, which means it's at 1000, which means it is square 1000, that's a million. So it's a million times, so it's, let's just say it's a million times slow, right? And if you go to 2000 and we square that, that gives us 4 million. So it has become four times slower. You could probably have guessed that in that we just doubled it. And so if you double it, that's times 2, and then you square 2, you get 4. So it will be 4 times slower when it doubles. So how do you find one name in a 1000 page book if the pages are scrambled and we're using linear search? So this is the pseudocode for that. So you go from the first element. That's what the pseudocode is doing. For I from 0 to, so we are using an index, a zero index, which means that's what most programs use. Is a zero index. So we're starting from 0, something at position 0, something at position n minus 1, which n in that case is the length of the list. Right. So from I, for I from 0 to length of the list minus 1, if list I is equal to target, return I, else return minus 1, and then you keep doing that, you keep doing that. And so worst case, it will take you length of the list amount of steps, which is n. Right. So best case, that's the first thing on the list, and you needed one step, which is the constant time. So that's best case O of 1. Worst case O of n, it is the last thing on the list. And the memory space, you don't need to create any more arrays or any more to be able to do linear search. The space is O of 1. So it's constant space. You are not, the space is not increasing as the data increases in order for us to do linear search. So linear search requires no pre-sorting. Yeah, I already talked about that. I don't want to really talk more about much about data structure. So I don't talk about linked lists and such, but we'll talk about data structure when we begin the first cohort of this course. So yeah, so let's go down to the next one. So binary search. I already spoke about binary search. So there's this famous Harvard course where the lecturer tears a phone book, right? So a phone book is already sorted in alphabetical order, and so if you're looking for, let's say, Samuel on that phone book, you just divide the phone book into half and say, okay, it's S on this half or on this half. Then you throw away the half that S isn't on, right? And then you divide the book into half again and you check where's S, is it on the right half or on the left half? And then you throw away the other half, and then you keep doing that until you find what you're looking for. And that's what this pseudocode represents here. And so let me just go through it briefly. So binary search, it takes in the list and the target. So we're looking for Samuel right on the list, or let's use a number. We're looking for 7 on this list below here, right? And so we choose our low is 0 and our high is n minus 1. Divide that into 2. So while low is less than or equal to high, that's the prerequisite condition to run this loop. So we choose a midpoint, which is low plus high divided by 2. And then we actually have to round up here, but this pseudo code. So round up or round down, anyone works. So if the element at the mid position is equal to target, return that position as, oh, we have found this is the position of whatever we are looking for. Else, if the list if the element at the mid position is less than target, right? So let's say Samuel, or let's say 7 in this sorted list already. So we're looking for 7, right? And so or let's say we're looking for 1 in this array, right? And then this is our mid position, this seventh position, and then we divide it into half. We have 1, 3, 5, and we have 7, 9, 11, and 13. So our mid position here is 0, 1, 2, 3. So I've chosen 3, right? So if the element at position 3 is less than our target, which is 1, low should be equal to mid plus 1, right? So our low now, so now our this thing is 3, position 3. So what's our position 3? Is 7. Is it less than target? No. So we have to go with this one. So we have to adjust our high instead of changing our low, because we want to go from 1 to 7 now. That's the half we want to go with. So we have to adjust our high to this midpoint. So our high now will no longer be 7, because we already put this condition that if 7 was the answer, we should choose 7. So our new high now will be at this position of 5, which is 0, 1, 2. So now we are going from position 0 to position 2. We have reduced our sample space that we are searching through now. So we're only searching 1, 3, and 5. So we choose our midpoint again, which is 2 divided by 2, which is at position 1, which is 3. Is 3 target? No, right? So is it greater than or less than? It is greater than. So that means we'll move our high again from position 3 to position 1. So at this point, we have already gotten our answer, which is 1, because we chose 3 before, and now our new high now is 1, and our low is also 1. So which means we have found our target using binary search. And so this is a table of how binary search compares with linear search. And so if you have 100 steps, worst case scenario for linear search is 100 steps, and worst case scenario for binary search is 7 steps, which is 14 times faster. But look at how ridiculous that difference increases when we 10x our items, or 100x our items. this goes to 10,000 steps, and this only goes to, we did 100 times more data, and we only increased by double for binary search. So this is how fast our algorithm is, because it has logarithmic time complexity. And so you must understand, choosing the right algorithm is choosing the wrong algorithm on a slow computer. Choosing the right algorithm on a slow computer asymptotically, which means, for large amount of data, is better than choosing the wrong algorithm on a super fast computer. So you can have a bad algorithm on a super fast computer, and on this my PC here, if I do the right algorithm, I'll get to the answer faster than you. Right. So that's how important choosing the right algorithm for your specific use case is. And sometimes you can also see that when the data set is a bit smaller, sometimes choosing a so-called worse algorithm might be better. We'll look at that. So 10,000. So when we increase from 10,000 to a million, this goes to a million steps, and this goes to just 20. And when we get to 4 billion, this just increases a little bit by 12 steps, and then we get to just 32 steps to go through 4 billion items. So for instance, Kuda sort is 2 million accounts. So it has already sorted his account, so we can use binary search during the day before the alert system uses binary search. So if you have 2 billion accounts to go through, all we need with binary search is 21 checks. Meanwhile, if we're using linear search, we'll have to, worst case scenario, we'll have to go through this 2 million times. Recursion. Recursion is one of the like, it's a very difficult concept to understand. But when you understand it makes all the sense. Right? So recursion, this is just a joke. To understand recursion, you must first understand recursion. That's how recursion is a function calling itself, right? And so there are different ways you can implement recursion. We're not going to that in this class, but by the time we begin our first cohort of decoding logic for think.com.ng, we'll go into all those things. But there are different ways, even though it's recursion, that if you can implement a recursive function recursive recursively, or you can implement it what will I call it, iteratively. Yeah. So there are different ways to implement recursion. So we will also see that, right? So to be able to implement recursion, there are two cases that need to be there: the base case and the recursive case. The base case is super, like, this is how you conceptualize recursion. When you want to write a recursive function, this is how it's easy for me to write a recursive function. Is that I know, first of all, I just have to first determine the base case. Once I determine the base case, the recursive case will come to me, right? Because that's the easy part. The hard part is for you to understand your problem enough to be able to write or put down the base case. So, for instance, some of us know factorial. So, what is factorial? In mathematics, is you say n multiplied by n minus 1 multiplied by n minus 2. Programmatically, it is n multiplied by the factorial of n minus 1. But you're saying, but that's like, in English, they tell you, oh, when you're defining, it's just like me saying, what they say, what is culture? And I say, oh, the culture is the culture of. An English teacher will tell you, never do that. Never explain something with itself. Because how can you tell us culture is the culture of something, something? Like, that doesn't make sense. We are inputting the thing in its own definition. So we can't really grasp what you're saying. But in programs, there are many times you have to write a recursive function. And so, for instance, in factorial, which is, for instance, if I say 2 factorial is basically 2 times 1. If I say 3 factorial is 3 times 2 times 1. You are seeing the pattern. If I say 4 factorial is 4 times 3 times 2 times 1. So what is 4 factorial? 4 factorial is 4 times 3 factorial. Then what is 3 factorial? 3 factorial is 3 times 2 factorial. What's 2 factorial? 2 factorial is 2 times 1 factorial. So what is 1 factorial? 1 factorial is 1. And that 1 factorial that is 1 is our base case. So that's why in our pseudocode we have if n is equal to 0, return 1. Sorry, n factorial is 1 minus 1 multiplied by 0 factorial. And what is 0 factorial? 0 factorial is 1. This is not math. I'm not going to prove to you why 0 factorial is 1. But there's a proof. You can always search. So or you can join our math class for that. So that's what that's what recursion means. So if somebody says what is 5 factorial, you can just say 5 factorial is 5 times 4 factorial. And then you can keep reducing it until you get to the base case, which is 0 factorial. And so that's why we say if n is equal to 0, return 1. That's our base case. Those it is you cannot write a recursive function without a base case. So now we have identified our base case. The recursive case is return n multiplied by factorial of n minus 1. So now you can see the example of 4 factorial. 4 factorial, 4 times 3 factorial. The computer stores that. Now, next step. Okay, so what is and now it goes to expand. What is this 3 factorial? This factorial of 3. And then it runs the function again. And what the function gives us as the factorial of 3 is 3 multiplied by the factorial of 2. Okay, so it goes back to the function. So what's the factorial of 2? And input 2. And now the function gives us the factorial of 2 is 2 times the factorial of 1. And then it goes again and says, what's the factorial of 1? And so the function gives us that it is 1 multiplied by 0 factorial. And then it inputs 0 in that case. And then that's when our base case triggers and says, okay, n is equal to 0, which is 1. And so 0 factorial is 1. And so we get back this. I'll still, when we begin our cohort again, I'll say it again. I will explain to you how how you can conceptualize this. How does the computer actually think about this calling or this recursion and things like that? How does the computer actually handle it? It may not be exactly how you think the computer handles it, and there are multiple ways to conceptualize. How you conceptualize the implementation does not mean that is what the computer does. So sometimes we just have to build mental models of how we think or our own idea of how the computer is handling these things so that we can work with that concept. Not That's not primarily how the computer does it. Right. So um let's yeah, this is what we're talking about, the structure of oh you keep putting that into a stack, right? 4 factorial, 3 factorial, 2 factorial. We have not yet executed it though. It's now when we get to that base case of 0 factorial, then we execute everything. Then we execute 4 times 3 times 2 times 1 times 1 equal to 4. So we just keep storing it in that stack frame, stacking it factorial 1 factorial 2 factorial 3 factorial 4. And then when we get to the end of it, we execute. That's one way to conceptualize the implementation. So how would a child sort a hand of playing cards? Okay, yeah, I got carried away. My brain is falling. So, how would a child sort a hand of playing cards? Right? So, the way the child sorts is okay, I have I've forgotten what's the maximum you can get in what? Is it 20? I think 20. That's the I need. So 20. This is 20. Keep it here, or keep it to the right and say this is the maximum. And it says 14. Keeps it. It sees. It looks. It checks whatever it says. It just keeps. Just keeps going through. Or if you want to sort it from the smallest to the largest, you can just go 20 and put 20 at the back and keep looking until it finds one, and then put that one down. Then keeps looking till it finds two, and that's how selection sort is. So you can also to get the big O of selection sort is also very intuitive. I say it's also very intuitive. It's actually not that difficult to be able to just okay. So for instance, selection sort, we are going to go through the array or the data n to the n. I'm using n as in the length of the list that we're going through. So we're going to go through this n number of times, right? So we're going to go through this n number of times. And then how many? So for instance, like on our first step, what we'll do is, so let me go to the pseudo code. So from I from I equal to 0 to n minus 2, right? So for instance, we have a list of 7 things. We are going from 0 to 5, and you will see the reason for that. That's 0 to position 5, right? And then in our second loop, we'll be going from 1 to 6. So let's just go through this first step. So we are going want to sort 5 3. This is selection sort. So we want to sort 5 3 1 4 2, right? So we go from what is in from position. We go from 1. So we choose a min index. So our min index now is 0 for this first step, right? And so the condition is if and our j, so our min index is what? Is 0. Our I at this point is 0 too. Our j is what? 1. And our n minus 1, how many do we have here? 1 2 3 4 5, which is 4. Our n minus 1 is 4. So we are going from, in our first step, we are going from 1 to 4. So if the element at position j, which is 1, position 1, that's 3, is less than the element at position, our min index is 0 at position 1. So we are checking 1, 3, and 1. So if that is less than, right? So if 3 is less than 1, our min index will be 1. So we check, is 3 less than 1? No. If 3, so since 3 is not less than 1, we swap. We swap, we check 3 and 5 rather. So is 3 less than 5? No. So we swap 3 and 5, right? So we swap 3 and 5. Then the next step, we check 3 and 1, we swap. The next step, we check, sorry. Oh shit. I think there's an error in this, in the way they wrote this thing. So which is confusing me. So let me just do it myself. Okay, so we have 5 3 1 and 2. So the first step, our I is 0, and that's also our min index, right? And our j is 1. So we are going from j equal to 1 to j equal to 4. And we are checking what is our position j for the first one, which is 1, which is 3. So we are comparing 3 and 5. So if 3 equals to 5, then our main index will change to 1. But 3 is 3 is less than 5. So our main index now is 1 instead of 0. So that's 3. So we go again. Then we swap 3 and 5 swap. We go again. 5 5 and 1 swap. 3 we now have 3 1 3 1 5 4 2. Then we check again. 5 and 4 swap. 3 1 4 5 2. 5 and 2 swap again. 3 1 4 5. I mean 3 1 4 2 5. Then we take 3 when we go back here again. So now 3. Then we check again. 3 and 1. 1 is smaller. So we swap. 1 3. We have 1 3 4 2 5. Then we are checking 3 and 4, which is smaller, 3. Then we leave it. We go to the next step now. We take, so 3 and 4, sorry, which is smaller, 3. We go 3 and 2, which is smaller, 2. Then we swap. So we have 1 2 3 4 and 5. End of it. So you only took 4 steps to be able to get that. So comparison. So how is this n log n? We have to do this inner process is log n. But how many times do we have to do this inner process of swapping? We have to do it n amount of times, which is from 0 to n minus 2. And so even though it is not particularly n minus 2, it's actually, we are going to do it n times. This inner one, we are going to do it n minus 1 times. And so the outer loop runs n times. For each pass, the inner loop scans the remaining elements, right? So which is n times, and the inner one runs n minus 1 times. So and then we have that what will I even call it? Summation of a is it a sequence or a series now? I think geometric series, right? So which is n multiplied by n minus 1 divided by 2. So and in big O notation, we drop all our constants, and basically we have n squared over 2. We still drop our constants, so we have basically an O of n squared, right? O of n squared, that's quadratic, so which is pretty much very slow. So merge sort. So for merge sort, we split. Is one of the there are many algorithms that are under this category of divide and conquer, and one of them is this merge sort. And so, for instance, in this case, we have 314,159. We break that into 314,159. We break that again into 314,15 and 9. Now, the thing on the left, we call that position I, and the one on the right, we call that position J. So we compare I and I. So the I of 1 and 4 is 1. The I of 3 is 3, because that's the only thing there. We compare which is less than 1. We put 1 first, then we put the I here of the second one, which is 3, and then we put our 4. The same thing we do here. We compare 1 and 9, I and I, which is less than 1. Then we compare 9 and 5, and then we get 5, and then we get 9. Right? So that's how it works. That's how measures work. We keep on breaking, divide, and then when we get to this last step, we compare I and I, right? I and I, we get this 1, and then we compare again 3 and 4, we get 3, and then we get 4. Then we compare again 1 and I, we get 1, 5 and 9, we get 5, then we get 9. And so when you now put it together, you will now see that it is already sorted. So it is 1 1. You compare I and I, J and J, then K and K. And then you get 1 1, 3 4 5 9 sorted already. And so the two things that we really worry about, so let me just close this class here because of time. So the two things we're not able to get through those slides, but the two things that we mostly worry about in programming is time and space. So those are the two constraints. So you don't want to take you don't want to use an algorithm that takes too much. And I'll also let me quickly explain there are scenarios where you might use a worse algorithm because the size is small. This big O that we're talking about, quadratic, linear, those are most of the time we are concerned about the asymptotic behavior. And what I mean by the asymptotic behavior is as n grows larger. So sometimes when n is small, there are some algorithms that even though they are worse asymptotically, they are better because the sample size is small. But when we now grow larger, that's when you have to just simply compare the big O. Sometimes something might have a worse big O, but if you are just comparing 10 things, it might have a better performance when we are using small amount of data. Do you understand? And so you must also understand how to choose your algorithm and not just say, oh, this is faster. You must understand in what case is it faster and in what case can we use this algorithm or that algorithm. And so that will be the end of the class for today. And when we begin our cohort, we would announce that so that people can register. And we have divided it the all courses into different modules. And so me, I'm more concerned about the teenagers and the younger generation. So that's really what I'm concerned about. I want them to be 10 times better than we are now and have better teachers than we did. And so we are going to tie all this up to, of course, I can teach you for instance, if we are talking about chess, I can teach you all the rules of chess in 10 minutes, 5 minutes, 4 minutes. In 1 minute, I can teach you all the rules of chess. But that doesn't mean you're a master chess player. I know all the rules of chess. Magnus Carlsen knows all the rules of chess. But me and Magnus Carlsen are not on the same level in playing chess. So, of course, I can teach you all the rules of programming and but that doesn't mean you're now a master programmer. No, you're not. It is how you combine those rules, how he, Magnus Carlsen takes advantages of the chess rules. He takes advantages of the movement of the pieces. That's what differentiates us from him. It's not because we do not know the rules. And so I can teach you all the rules of JavaScript within a couple of months. But that doesn't make you a master JavaScript programmer because it is how you combine those rules, the structure and the implementation that will define that. And when we begin our cohort, I think we'll be able to take people from the beginner stage or whatever stage you are in to a stage of where you can actually combine the rules and the structure of programming languages to get your implementation, be it machine learning or apps or whatever the case may be. So that's it for today. Thank you all. Boom, 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 boom.